All right, everybody, welcome to Earth Science. If you look at these two, and I think some people probably are kind of cozy with where we're going with this. We're looking at latitude and longitude. We want to try to at least notice before we get too started on it the basic difference between like the two, just as shapes, even before you get into the Earth Science part of it. So what are some things you notice over here is what I would be asking you if we were here together. These lines are parallel to each other, whereas these lines converge at the poles. It's a big difference. Like, and again, it's just visual. Like, look, they all come together there, they all spread apart, they come back together over here. These, parallel, 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 parallel. You can refer to these, in fact, as parallels. They'll call lines of latitude, it's maybe slightly outdated language, but they'll call lines of latitude parallels. They'll call these sometimes meridians. Let's throw it in there. What the heck? That won't hurt anybody. Parallel, so they're called parallels. Whereas converge at the poles, these ones are called meridians. Perhaps you've heard of one special meridian. In fact, it's written right there. So great. I mean, that's really what they are. These are latitude. These are longitude. And some other stuff indeed. So yeah, these go east-west, like direction-wise, right? These go north-south direction-wise. But maybe the weird thing that we'll get into is that although these go east-west, they tell us how far north or south we are of the equator, whereas these that go north-south tell us how far east or west we are of the prime meridian. So hopefully you did your homework over the Halloween weekend, and you looked and you saw Polaris at some point. If not, I'll do a second little go on what you got to do to find it right there. And let's make this bigger. What we're going to do, this is tricky to see. And I know I'm not here, but this is how I'd explain it here if I was. If you live here on the equator, to look at the North Star, this North Star is ridiculously close on this diagram. It's not to scale. Nothing's to scale. It's like trillions of miles away. So if you were at the equator, you're going to look like that to see it. And if you're about where we live, which is like halfway between the pole and the equator, you're going to look in a parallel line to see it. And if you were at the pole, you're looking at another parallel line to see it. No matter where you are, you're looking up to see Polaris way the heck off in the distance above the North Pole. If you can, you're going to nail this stuff. See that angle right there is really small, and then that angle right there gets bigger, and then that angle gets much bigger, so big in fact, I should draw a square, right? So big in fact it's a right angle. So as you get further north, the angle you look up at to see Polaris gets bigger and bigger and bigger. If you can see that relationship, I should probably write that here too. You guys are going to get a better version than the morning class did. As you travel north, the altitude of, learn to spell, of Polaris does what? It gets bigger and bigger and bigger. It increases. And in fact, this is deceivingly simple. If you want to know exactly what latitude you're at, you do your homework, you find Polaris. And the part I didn't tell you that is that whatever angle you look up at to see Polaris, that angle right there, so this guy with this hat is looking up at an angle of 66.5 to see Polaris. Guess what his latitude is? 66.5. No math involved. That's it. So there's these kinds of things. You'll see people like on TV shows or cartoons using this to make it look like they know what they're doing. You can look through here, you can adjust these little mirrors, and the principle of it is that you'll be able to look up and see what angle Polaris is. You can make a really easy one out of a protractor with a little string hanging off of it. No matter what, it's the simplest tool for telling a complex thing that I can think of, right? It's just look up and find the angle. The angle of Polaris equals latitude. That's it. So do it. Like, do your homework. Go try to find Polaris. I've said a couple times, if you can picture where I am in the room, that, hey, I'm pointing at Polaris right now. The ceiling's in the way. It's daytime. It's cloudy. But it's there because I know where north is. I'm pointing north, and I'm pointing up at what I know our latitude is. So granted, I already know, this because I know where the school is. But if I were in the middle of the ocean in the middle of the night and you were in the northern hemisphere, I could still figure out my latitude. It's easy peasy. So the Big Dipper moves, does the circumpolar thing, goes around Polaris throughout the course of the day. Those two stars at the end of the scoop point to where Polaris is. Doesn't matter where it is. It goes around 24 hours. It goes all the way around. I know some of that's daytime, but that's how you can find it. And then the answer is that simple. We'll write it again over here. The angle you look up at to see Polaris equals latitude. Dunskies. So early maps, and if you want a book on the history of maps, I've got some good ones. Early maps were very, very, very accurate north-south, because I'm telling you, I could put you in the middle of the ocean with a straw, a string, and a protractor, and you could find your latitude. Longitude was way, 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 way harder, because there's not like an easy reference like the North Star. There's no East Pole or West Pole. That's not a thing. The planet spins all the way around the pole like this, but all these longitudes got to pass underneath the sun every day. So either you don't know what time it is, or you don't know where it is, or you don't know where you are, or you don't know both, right? So hop into a boat, go sailing off into the middle of the Atlantic Ocean, unless you know exactly what time it is. Before there were watches, you didn't know, unless you knew exactly where you were. You're in the middle of the ocean. There's nothing you could do. You couldn't do east-west. You could do north-south, and again, those maps were really great, but they were terrible east-west. So it kind of works with time. It's like a function of time. It's harder conceptually to understand, too. It's a function of time / like sun moving across our sky. I don't know what that was. So a sundial, if you've ever played with one of those, I know there was like kind of a bootlegged one over at Boaters Beach for a while with just a big log stuck into the ground and you saw the shadow through the course of the day. A real one, you'd have to like make it and point that right at the pole star. Easy to do because you know your angle with your latitude. And the shadow at solar noon would be highest, and you call that noon. And then after noon, after the sun's through your meridian, or before the sun's at your meridian, so ante would be like the before part. So ante-meridian is how we got AM. Post-meridian is how you got PM. So post-meridian, the sun has gone through the afternoon part of the sky, past solar noon. Not easy to picture. Stick with me, though. You'll figure it out. Once they got clocks on ships, they figured this out. It's actually the reason Darwin was traveling around the ocean when he figured out this whole evolution thing. That's another story. But they had clocks on that ship. They got around and they did a very accurate job of mapping some areas in South America for navigational purposes. Now, what we did, it used to be one of these was good enough. Nobody had clocks. Nobody could travel longitude-wise very far anyway. So, like, everybody's meridian, if you consider Pulaski's meridian, right? This is my south wall. That's my north wall. If you did a line from the South Pole over my head all the way to the North Pole, that's me. My solar noon will be when the sun's at the highest point, and then that's fine. Later time zones, like over towards Buffalo, won't get the sun till solar noon till a little bit later, but I can't get to Buffalo very fast anyway, because historically there was no trains or planes or cars yet, right? By the time in those days I could get to Buffalo, who cares if that noon's a little bit off from my noon? Till they invented trains and you could move fast enough. Then they had to say, hey, we can't have trains running into each other, which they were. They had to figure it out. So they said, let's take the Earth, and it's 24 hours, and it's 360 degrees of longitude, and maybe, hopefully, those numbers sound familiar. Maybe you know where we're going. We arrive at the number 15 again. Every 15 degrees, they said, let's put in a time zone. So right now, according to this clock when I recorded this is 10:30 in the morning, right? Note this. The planet spins that way. That didn't come out red, but whatever. And again, longitudes are all kind of a function of how we spin underneath the sun. So every 15 degrees needs its own time zone now. And then they had to kind of wiggle it around population centers and things like that. You don't want a time zone on one side of a city versus another or something like that, right? So they do it like this, about every 15 degrees. You got 10:30 here, so we've got the sun up already because the East Coast is moving forward that way. It's not going to come up here for a few more minutes. So they're a little bit later there. It's 11:30 right now in my old hometown of Minneapolis. It's, well, I went the wrong way. It's not my day, folks. Welcome to Earth Science. It's earlier in the morning because the sun has not come up yet. It's 9:30 in Minneapolis. My other former hometown, let's hope I do better here, is another hour behind. In Netherlands, it's only 8:30. And I've never been to the West Coast, but our friends on the West Coast there, it's only 7:30 in the morning. And think about what that means for sunrise. The sun is like coming up as the planet spins that way, so they just haven't got it yet as much as we have. And then by the time the sun goes down for us, because the planet has gone and spun off that way, these guys still have the sun for a couple of hours before it goes away. Cool. And really, I mean, they might make you do that, and you might make a mistake like I did and go the wrong way, but count your time zones 1 per hour every 15 degrees, and you'll be fine on those questions. They usually are no big deal. All right, nuts and bolts. Let's just bang out a little bit on each one of these. Latitudes. The lines are all parallel. They never touch across. That's just how they work. They can be called parallels. They're based on, get it down, the altitude, however high you got to look up to see Polaris. And these fancy tools or the simple protractor tools can do that job for you. We'll see how the week goes. If it's smoothly, maybe we'll make them late in the week. They go from 0 degrees to the equator. The equator is 0, so you wouldn't say north or south for that. But all the other ones you will say either north or south. So from 0 up to 90 degrees north at the North Pole, or 90 degrees south at the South Pole. Yeah, no such thing as 95 degrees latitude. Longitude. All meet at the poles and loop around the whole planet. This important one, and this is kind of more interesting historical map stuff for some people. There was kind of a fight over the prime meridian. Who got to be 0 degrees longitude? Other countries and civilizations at the time when we were starting to make world maps all kind of said, I want it, I want it, I want it. And the British won the fight, which if you know your history, shouldn't be surprising. The prime meridian is what they call it. And there's nothing earth science-wise about that. It's purely a historical fact. They said that this is 0. There's a little brass plate in the ground or something. This is it. We British want us to be considered 0, and everybody is either west or east of England. Not we British, my bad. That's what the British said. Longitude lines, therefore, are close to the poles. If you want to walk all 360 degrees of longitude, go up to the pole to do it. Bang, you can do it in 3 seconds and far apart at the equator. If you want to walk all 360 degrees of longitude to the equator, you got yourself quite a trip. All right, now this is potentially frustrating. If life were easy, we've brought this up before. Degrees are broken into minutes, and minutes are broken into seconds. We did it when we did the angular size of the sun. It's the same deal. It's the same deal with all angles. It's the same deal with these degrees of latitude. So if life were easy, I wouldn't be talking about it, this part at all. We would just say that is 43.5 degrees north, right? But life's not easy. Because what we got to do is say it's some number of degrees and some number of minutes. And if the map were zoomed in more, we could also say some number of seconds. So that's what we got to bring to the party here. We got to break them down into minutes and seconds. And each degree has 60 minutes. So you like lose the decimal system. You got to go by 60s again. And then each minute has 60 seconds. Again, we're not likely going to deal with that this year unless you go really close on a topo map. So what would I really have to call that line right there? 43 degrees. That part's easy. And we already did that right. But it's 43 and a half is not wrong. But now what would the half be? Is like, there's 60 in the whole thing, so like 30 minutes. That's what it should look like, other than forgetting to put north. Okay. So with that in mind, and this, I would normally pause and say, okay, everybody tell me what is the latitude of that line. Think about it for a sec. What would it be? Maybe you get it. Pause if you want to think about it. 42 degrees, because from there up to there. And now halfway would be 30. This looks like it's about halfway between the 30 and the top. So that would be about 45 minutes. Sorry. Deal? All right, with that, what you're gonna have to do is go to, different people will be hitting this at a different time. I know there's a sub here today. I'm gonna have you grab the map from the sub. They know what to do, they know what to give to you. Find 2 different colored pencils and find a ruler. I'm gonna pause while you do that, go do that, and we'll come back. Okay, so you've done that, you've got both colored pencils. Here's what you're gonna do. With your ruler, make a nice neat line. In fact, I could use the line tool here, I suppose. Maybe. Yeah, I'll just draw it. 45 to 45. We're going to start with the latitudes. So with one color, I'm going from 45 to 45. Your line is probably going to look better than mine. And then we're just going to go down the latitudes, one for each. From 44 to 44. From 43 to 43. From 42 to 42. And from 41 to 41. And that's it. 40-30 is here, but we don't get as low as 40. So that's like halfway, but you got those on there. That's a good start. Pause if you need to catch up. I'm going to go over and do the longitudes. I think it's going to be easiest if you start over here on the left. We're going to start with 79. We're going to go to 78, 77, and so on. I meant to switch colors. I didn't do it. If you want to do that in a different color, it might be easier for you to use. $75. This one's getting terrible. You guys know what I'm doing by now, though, right? $76, $75, $74 is way down here. Watch out for that $73.30. I don't know why they only did one of those. The 73 should be right there. And 72 is kind of weird. There's only one of them, but you can kind of picture where it is and make it look like that. Now, hopefully yours looks better than mine. Wouldn't take much. But that's it. That's the grid. We live in the northern hemisphere, so these are all latitudes north going up. We live in the western hemisphere, so these are all western hemisphere, western longitudes, but note they count up going that way. That might be the only trick. So if you had to do Ithaca, I did this as a practice one with everybody. What you would do is say, where is Ithaca? Well, Ithaca's at 42, and then how many minutes up is it before it gets to 43? Again, it'd be from 0 to 60. It's not quite at that. There's a little mark right there for halfway, right? It's not quite there. So in the morning classes, we said that Ithaca was at 42 degrees, right? Because that's that line. We ballparked maybe 25 minutes north latitude. And maybe I should say this is Ithaca. Longitude, keep in mind you're counting up going this way, so it's at 76 degrees. And then how far over? It's almost halfway. It's like maybe barely shy of it, so maybe 29 minutes west. That's one example. Now, when we finish all of this, you're going to go back and try a couple others. Let's do this one, though, first. Let's do the same thing. Grab your rating, your colored pencils. We'll remember to switch this time. You're only going to draw one latitude, and it's 0. It's called the equator. I got to figure out the line tool on this thing. There we go. Way neater. Look at that. That's it. You're done with latitudes. But we'll note that as you go up that way, you're in the northern latitudes. As you go down that way, you're in the southern latitudes. Now we'll switch colors. We'll go bright green. I'm going to do this longitude. Remember what that's called? I'm going to label it PM. If you don't remember what that stands for, go back to the notes, check it out. We got to also deal with the back of that line, the PM line, if it's like a great circle. Let me grab my globe. Let's pause. So if the prime meridian's over here on the England side, well, what's the back of that great circle? How do you make the other side of it? Prime meridian 0, go all the way to the other side, and you're going to be here at 180. What I've done in the other classes is a dotted line. I don't know if I can do that. Oh, look at that. So at 180 degrees, this is called the international date line. I know it's a lot to write in a tiny little space, but international date line. It feels a little bit confusing because, well, we got 24 hours to split up, right? You can't go like from 1 hour off of the date line and then come back around and still be just 1 hour off of it. You got to have that be 2 different days. That might be a mind blower. I don't get too wadded up in that right now. Let's just say it's over there. Now what this gives me, believe it or not, are 4 segments. It looks like 6, but it's really 4. Because the way that this map projection is designed is to like spin around. So you see how Africa meets Africa right there? This line is this line. So what we've got is the western longitudes where we live, counting up from England that way to the international date line. And then typical crazy New York, for some reason they decided it'd be great to do the first 20 degrees of eastern longitude here, leave the map and come back on like Pac-Man, and do the other 160 degrees of eastern longitude here, giving you section 1, section 2, section 3 is this one and this one, section 4 is this one and this one. All right, so it's easier because there's not minutes on it, but you've got to just like say, hey, the Yellowstone hotspot looks like it's about maybe, I don't know, 45, 46 degrees north and maybe about 120 degrees west. It's a little probably easier to deal with because this one is more zoomed in. That said, if this is the right thing, pop back and try these. All right, so these should be all done to the minutes and seconds. Don't forget norths and souths and east and west. These ones are all north and west because we're in New York. Down here, find same deal, but you don't forget on the nearest minute, and you will need both north, south, east, and west, depending on which one. And if you get all of that done, then there's also a crossword to check out. All right, thanks for your patience, folks. I know that's a long video. I appreciate you. Good luck.